not all engineers think like hackers, and not all hackers think like engineers. And especially for an audience like this, where we're designing products that are going out in the marketplace or that are being used, we kind of have to think about what hackers are going to do to our systems, because it's only a matter of time, right?
Hi, everybody, and welcome to the OnTrack podcast. I am Zach Peterson, guest hosting for Judy Warner, and today we're going to be talking IoT and hardware level security with Joe Grand. I'm very excited to be talking about this as it is a contemporary topic, and I'm hoping everybody learns quite a bit about hardware level security. Let's go ahead and get started.
Welcome to Altium's OnTrack podcast, where we talk to leaders about PCB design, tackling subjects ranging from schematic capture all the way to the manufacturing floor. I'm your host, Judy Warner. Please listen in every week and subscribe on iTunes, Stitcher, and all your favorite podcast apps. And be sure to check out the show notes at altium.com/podcast, where you can find great resources and multiple ways to connect with us on social media.
Hi, Joe. Thank you so much for joining us on the OnTrack podcast. I know that you are an AltiumLive alum from some years back. I know that Judy is out of office right now planning for AltiumLive, and for any listeners who are interested, we've got a registration link down in the show notes. Hopefully you can come back again at some point in the future. But I was actually really interested to talk to you after watching your earlier talks and watching a video about you. And you came recommended by some other folks at Altium. So thank you again for being here.
Cool. Yeah. Thanks for having me. And it's been a while. I think my last OnTrack podcast was with Judy a couple years ago, and I looked a little bit different. That was pre-COVID hair, and now this is the post-COVID hair. And I'm glad to be here. I think
I know all about COVID hair.
That's right. Altium has been a company for me that actually has been one of the few companies that have stayed the same as far as the tools I've used for a long time. And without sounding like a marketing pitch, it's like anybody that's worked with the tool, it's like once you start using it and you get used to it, you're kind of stuck with it. So no matter what you do, I'm going with Altium, and I don't really have a choice at this point, because all of my previous designs, over the past basically 30 years, starting with like ProTel Easy Tracks, actually ProTel Free Tracks and Easy Tracks, and moving along through there, and Altium and then Altium Designer. I appreciate what you all do, and I appreciate that you're having me on here, and hopefully people find it interesting. And if you're out there listening, thanks, and it should be fun.
Yeah, you talked about ProTel. That was a little before my time as a designer. I never got to use ProTel. I think I was still an undergrad at that point. But now jumping into Altium, I totally understand what you mean.
Yeah, and it's like it's like if you're writing code, you have your code snippets that you always use, and my footprint library that I've designed is massive. Even though now you can, there's a lot of good options for some community driven component libraries and things like that. But I just have my go-to set. And the first thing I built, talking about hardware security, the first circuit board I ever designed using free tracks was a little op-amp board that would take in the audio output from a radio, from a ham radio, and decode pager traffic. So the POC-SAG pager transmissions. So it'd basically be the op-amp that would amplify the signal and kind of provide digital data into a computer, and then there'd be software on the computer to decode that. So it was like a little kit that I sold when I was part of a hacker group back in the day that would help pay for the rent by selling these circuit boards. And that was the first board I designed, and learned a lot, because even back then it was a panelized board, and the board was only like 1 inch by 1 inch. But even learning about component placement at that point, where I had before that only hand etched circuit boards, and it's kind of like you placed components where they were best routable by your rub off letters. And then I learned very quickly that when you're making a kit and other people are building it, you want to make it where the components are easy to access and make sense. And you can kind of route stuff where you want, especially if it's a 2-layer board or more. You have options there. So I learned just a whole lot about circuit board layout and design early on, and then from there, I'm but definitely by no means an expert. My passion has always been in kind of creating tools to kind of show a concept or to do something or to empower somebody. And I've laid out some what I consider fairly complicated boards, but to any like competent circuit board designer, probably most of the Altium audience, the stuff I'm doing is sort of like, not that bad. It's like micro BGA with some, maybe like a 6-layer with some blind vias and stuff like that. To me, that's like state of the art, but for most people, probably not, but it's still exciting. And then to be able to, kind of grow and use some of these more advanced techniques as somebody like me, it's really cool.
That's funny that you brought up your first circuit board was an amplifier-based board, because that's what mine was, and it was by no means sophisticated or shockingly complex. It's just a funny coincidence, but I had to actually pull in measurements from a lot of instruments and then put it into a GPIB-linked series of instruments and then hook that up to LabVIEW, and that was a lot of fun. And for me at the time, that was certainly the most advanced thing I had ever done with electronics as a graduate student, and then it just kind of took off from there. And now here I am.
Yeah, that's exactly it. It's like, trying to get things from the real world into some sort of format that becomes usable for something else, sort of the interfacing types of stuff. And yeah, in the other podcast, we talked more about my history and how I got into all of that stuff, but it's just so cool to be able to, at any level, have something in your head or build something that does something, right? And like, that's what's so exciting about it. And then the hacker perspective really is interesting to bring to the engineering world, because not all engineers think like hackers and not all hackers think like engineers. And especially for an audience like this, where, we're designing products that are going out in the marketplace or that are being used, we kind of have to think about what hackers are going to do to our systems, because it's only a matter of time, right? Like if your product is worthy, somebody is going to want to hack it at some point. And it's sort of like, there are a lot of things we can think about from a design perspective, even from a circuit board design perspective, layout perspective, and parts placement, all these things that could be useful, even if it's too hard or too expensive to implement, higher level types of security. So there's just so many fun things. And being a hacker to me is sort of like, I tell people, it's like people are always going to get sick. So being a doctor probably isn't such a bad thing if you're into the medical profession. People are never going to stop being sick, right? So with hacking, it's the same thing, or security, really. There's always going to be some security issues, and hackers, either good hackers or bad hackers. I kind of use the term as like both, because I grew up as a good hacker, and there wasn't really an intentionally malicious element at the time, and it wasn't like it is now, where there's the ransomware and groups specifically hacking to make money. So I kind of use it as an overarching thing. But yeah, hackers aren't going away. And, part of it's curiosity, and we like to mess with stuff. And then if it's the other element, if there's money to be made, there's going to be people trying to mess with products. So it's a great kind of world to be in, because you get to see so many things from so many different angles and so many different approaches of how to not only design hardware, but how to break that hardware that's being designed. And then as new products come out, or new chips come out, or new technologies come out, trying to figure out how you can still defeat those. So yeah, it's just like a never-ending kind of collection of things to do.
Yeah, definitely a game of cat and mouse. And I know that, these days, cybersecurity is top of mind. It's whenever there's a major hack, it hits the news. But it seems like there's so much that goes on under the surface, behind the scenes. You never hear about it just because it's becoming more and more common in the software world. But, one of the things that I think that brings up, especially as more IoT devices get deployed in the field and then the attack surface increases, is what happens at the hardware level, and what can designers do to implement some, like even just basic bare bones, like hardware level security. Like, what are some of the things that designers can do that are like the hardware equivalent of like Windows Defender, like what can people do? That's one of the things that I wonder about, like what's the basic antivirus program you can put on your hardware? And I suppose if you think about, a typical embedded system, there's the application level, something that might happen in the cloud or, in a command center somewhere, whatever it may be. Then there's your code level that's on the device and the application that you actually deploy on the device. and then there's the hardware itself. And so it's almost like, with software, you've got one big attack surface, but it's all, on the web. With hardware, you've got three different attack surfaces, right? There's the code level, the application, linking it all together, and then the hardware itself. I mean, are the challenges and the thought process behind designing for, trying to protect devices that are in the field any different?
Yeah, I mean, that's a great point. So if you think about hardware products, they are basically, for the most part, general purpose computers running specialized code, or generalized systems or even a specific system doing something. It's a computer. So not only do you have the physical hardware stuff that we can talk about, but like you mentioned, you have the firmware level or software level, which is the code running on the thing. And then you have usually some sort of connectivity side. So whether it's a network connectivity at some point. So you have these three levels, and there's usually different people, depending on the size of the company and the product being built, there's different people working on those different levels. And I don't know how much communication is going on between those groups, but at every one of those stages, there are security things to think about. I also like what you said too about how, there are certain times where we see hackers in the news and we see a product being hacked or a database being released, or Twitter, Facebook, or whatever, some network related thing. It's almost to the point of like every day there's something. It's like, oh, but there's so many things that you don't hear about, and it's usually the ones that you don't hear about are the scary ones, right? Because if there's an attack that we don't know about, but some organization has a 0-day, so basically some known exploitable vulnerability on a product that hasn't been reported and hasn't been released and hasn't been fixed, those are extremely valuable. And that's a whole other world of like, if somebody finds a vulnerability, like somebody like me, if I find a vulnerability in something, if I happen to be hacking on something, I would report that to the vendor, give them some time to fix it depending on how responsive they are, and then go and share that with other people so they can better protect themselves. Sometimes vendors aren't as responsive, so you have to go kind of just full on open the kimono and release all the information to kind of force them to do something. But there are people that will find vulnerabilities and not release them and use them for their own advantage, whether it's a business advantage or financial gain or whatever it is. And those are the ones that you don't hear about. So you don't even know necessarily if you're being exploited or attacked in some way. So it really the whole thing is really hard to think about. If we want to talk about kind of like what can we do at a basic level, there's from a hardware kind of board level, I talk about like low-hanging fruit. And what ends up happening is there's so many things that happen anytime a hacker like me goes and approaches the problem. Whatever the product is, I always go through this set process, which is funny because you normally hear about hackers think outside the box and, they do whatever they want. And that's true, but coming from an engineering background, like I have my process that I go through, and then within those steps, maybe I'll branch out and, think about things a little bit differently. But just to give you that sort of idea, I kind of have like, an information gathering stage where I'm going, even before I open up the product, I'm going to find whatever information I can about it. So user documentation, information intended for the end user or for the customer, but then maintenance information, patents, certifications, marketing materials, press releases, all of these things that on their own maybe aren't a big risk or a big threat. But if I know that company X has partnered with company Y and uses all of company Y's chips in their product, now I know that I could, I'll target that company. And that's going to make it a little bit easier, especially in the case of if a vendor scratches the part numbers off the chips or something like that, or covers it in epoxy that makes it slightly harder for me to get to. By reading about this relationship, I already know, and I have a pretty good guess at what those parts could be. So information gathering is huge. Patents also, companies are protecting themselves with patents, not necessarily as a way to engage in innovation, but to protect themselves against other people doing those same things. And within the patent, there's lots of information about how the product works or how the security mechanism works. Certifications, even FCC certification, a lot of information becomes public about the test of how the system was tested, right? Your schematics, your block diagrams, photos of the system. And you can even search the FCC website, say by the vendor, and find things that were certified even before they're released to the market. So all these things that aren't even really, hardware hacking related, you can get a lot of information before you go to that level. So that's the first step. Second step is going to be to tear apart the product. So disassembling it in a way that we can get access to the circuitry. And sometimes it doesn't matter. Like sometimes we do that on one to figure out how it works, but then an attack might be that we find some vulnerability that's over the network, right? So you don't always need to take apart the product, but it helps to give you all the clues you need to then go do something else. Then component identification. And what I really look at is not only the components themselves, but how they're connected. Engineers and manufacturers are going to need things like test points and debug interfaces. And generally, we're going to see silkscreen markings on there for the part designators and sometimes for even other stuff, right? Because the more information that's on the board, the easier it's going to be for us as engineers to know what we're looking at, for manufacturers to know what they're looking at, so they don't have to reference other stuff as they're assembling or as they're reworking or whatever it is. And then for test engineers as well, the more information that's there. So we can take advantage of what's on the board to kind of know where we want to target. Another thing I like to do is look specifically at like buses and interfaces. So how chips communicate to each other, right? So if you have a microcontroller and some external peripheral, or you have a microprocessor and external memory, or whatever it is, you're usually, unless everything's integrated or you have an FPGA that's handling everything or an ASIC that's handling everything, you generally will have your main part with some peripherals. Targeting the communication between those things by using a logic analyzer and oscilloscope, basically standard engineering tools for the most part. There are tools created by hackers for hackers to make hardware hacking easier, but in general, you can just use standard engineering tools. So as an engineer, you can go through the same process to verify and think about, okay, if I'm a hacker, this is what a hacker is going to do. Let's see how easy it is to do, or let's see if we can protect it in some way. But looking at chip-to-chip communication, a lot of times, I2C, SPI, one wire, even if they're faster interfaces, they tend to be transmitting in clear text. So data that's coming across, unless you've built in some additional encryption of those data blobs, which sometimes you can't do because the peripherals that you're using just don't support that, right? So a lot of that stuff can be attacked that maybe we use in some way, and then we do some signal modification or spoofing or things like that. And then one solution that people are like, well, if we want to prevent people from sniffing buses on the board, let's just bury the signals on inside layers. And it's like, yeah, okay, you might be able to do that if it's a slow interface of some sort. But what if you're dealing with something faster that if you bury, now that affects your signal integrity of your system or of those signals or something. So the solutions to prevent some of this stuff and get rid of this low-hanging fruit are not always as easy as they seem. But that's the type of stuff, is looking at these things and thinking about, how do they affect me as the designer? How do they affect me as the manufacturer? And then how could they affect a hacker? Because a hacker is going to take advantage of anything that the engineer puts on the board to make the engineer's job easier. It's going to make the hacker's job easier. And that's what I sort of that's what I consider like the simple types of stuff. And we can go into all sorts of other things about component placement, component access, and all these other things to think about too. But it really is like starting with the most obvious things. And the problem is, stuff like debug interfaces and test points, we know we need those, right? And like, okay, then do we do password protection on it? Do we disable it, enable code protection, or disable the debug interface after manufacturing in hopes of preventing an attacker from getting access to that? But yeah, then you could do fault injection to re-enable that. And you're kind of at the whim of the chip vendors and how they implement security properly in order to give you security properly. So it's a whole mess of wires at that point.
So, what I'm hearing here is that and tell me if this is wrong, but what I'm hearing here is that you're actually looking through the hardware and scanning the hardware to see what type of data you can pull off to figure out what is your other way in. Because it seems to me that, if you have a device deployed in the field, maybe it's connected to a network, there's an application running somewhere, you're not necessarily interacting directly with the device at the end of the day. I mean, maybe you are. Maybe you go out in the field somewhere and, just mess with the device. But I guess if you wanted to disable something and you're in the field and you find it, you could take a hammer to it. But if you wanted to, really take over a piece of equipment and still have it be operational, you need to know what it's doing on the device. And then also, how does it interact with its end application somewhere else?
And I think it really depends on the product. Like, some people don't go through the detailed steps like I do. I just like seeing the physical layout to get a better understanding of what's happening. But if if a hacker is more skilled in software, they might just extract the firmware and go straight to looking through the firmware for problems. Or if it's like a Linux-based system, for example, you pull off SPI flash, or you pull off the SD card or whatever it is that has the kernel and the file system, and now you do all your software tricks on that device. So you don't have to necessarily always go to the physical board level stuff. I just think it's all about gathering clues and getting more information about the system, and that's what I like, but you don't need to. And if you have a network application, for example, or like an IoT connected something, if you can monitor network traffic and you see what it's doing, then maybe you inject things or you find a vulnerability in the network configuration or other stuff. But I do think that going through the steps is typically, if you have the time and the energy to do it as a hacker, is what you do so you can get as much information as you can. And that's what I end up, when I teach classes about hardware hacking, I sort of explain that of like, this is not always required, but the more information you get, the more clues you can get are going to help come in later, I think, when it's time to go do something else. And one good example of that is like, say you have a system that has some hard-coded credentials to log into some server on the back end or something like that. If you can get those from the physical memory of the device on the board, now you have those credentials, assuming they're not updated and changed. Now you can use those to do some other network attack, either acting as the hardware or sending data in some other way or accessing the network outside of what that device is supposed to be doing on the network. So there's all sorts of other things, but it's like you get these little nuggets of information that are probably useful later on. And it's important to think about that from a design perspective of like, okay, we're doing an IoT device, and you almost always want to assume that somebody will get physical access to your device and get information off of it to get those clues, right? So and people always say, well, if you get physical access, then game is over, but you can still make it harder for the attacker. But it's almost like when I use my computer, I assume that my computer is compromised in some way because I travel all over the place. I do take security precautions, so please don't try to hack me. But I kind of assume, okay, it's probably compromised, so I'm going to behave accordingly. And I think as a designer, you want to assume, okay, my product will be looked at. It will be tampered with, and proceed accordingly. If somebody gets physical access, does that matter? Maybe, maybe not. If they are going to get physical access and say, I do have some credentials or an encryption key or something I need to keep secret, let's think about that and say, okay, if I know that somebody is going to attack my system to try to find that piece of information, let's think about how we can better design our system to prevent that. So maybe instead of using an off-the-shelf microcontroller, a general purpose one, you're using something that's advertised as a secure microcontroller that has some secure elements with some internal memory storage specifically for encrypted elements and other things. But if you don't know that in advance, if you don't know that somebody might get physical access and try to extract information, you won't know as a designer to even consider using a secure device. And that's why I think just thinking like a hacker at all stages of the process, engineers and management and levels above that should all be thinking about this, because you can only anticipate so much, and the things you can anticipate, you should try to implement or make harder to attack at some point.
Yeah, it sounds like thinking about what are like the 2 or 3 areas of the device that are most important to protect, because from what I'm hearing, it sounds like there are some areas of the device that you don't really need to worry about. Like, the obvious one would be like a power connection or something. Who's going to hack you through the power connection? But maybe the other one is, part numbers. Do we have to scrub every part number? Maybe not. So thinking about those areas that are, most critical.
That's right. And usually you want to, and that would be called like a threat model is what we call it in fancy cybersecurity world. And that basically is thinking about how somebody could attack your system, and then you decide what's worth protecting. So, if I'm designing a security system for my house, for example, which is what I did, I would say, okay, if I was going to break into my house, how would I do it? Where are the entry points? Where are the exit points? So, okay, I'm going to try to protect those in some way. Where do I put my cameras that's going to catch, or motion sensors, I should say, inside of my house that's going to catch somebody, even if they don't go in the traditional entry and exit points, I'm still going to find them, right? So you threat model all of this, and then it's like, how likely is it that somebody's going to climb up to the second floor and go through the window? And you kind of say, okay, well, I don't need to put an alarm on every single window, because if I put the motion sensor, that's going to catch them. So you think about all these things. That's what you want to do from a hardware perspective, also from a product perspective. Okay, if I'm a hacker, they're going to go for the debug interface. So if you get access to, say, JTAG or a vendor-specific debug interface on the board, that can be pretty damning, right? That's kind of the root access, the administrator access to the system at that point. If you can single step through your code, and you can change memory and change registers and do everything on the fly, an attacker is going to have complete control. But we know that we need those things for manufacturing. So the solution is like, okay, let's see if we can lock that down. How does that affect us in the future? How is that going to affect repair? So we just have to model everything. And what's hard is nothing's 100% secure. It really is this cat and mouse game between how much time and effort is required to gain access to the system, and is gaining access to the system worth that amount of money, time, effort, etc. And you have to think about that for every product, because every product is different. And if it's, say, an IoT device that maybe is like a cheapo webcam, you might think, well, it doesn't matter if somebody hacks it. But then you end up with something like the Mirai botnet, where there's all these insecure IoT devices that were hacked with default credentials and things that just weren't secure from a network perspective. On their own, it doesn't matter if they're hacked, but now when somebody has 1 million of them, they can be used for a distributed denial of service attack or something else. And you don't want to be that company that is responsible for being hacked and being used in some malicious way. As far as power supply, I will say, because you mentioned, well, usually you don't have to worry about power supplies, but sometimes you do. And there's a whole other world of more an advanced hardware hacking technique called fault injection, where you're basically forcing the system to misbehave in a way that's beneficial to you. And this mostly comes into play when you're trying to defeat code protection of a chip, either to prevent reading from flash memory, or it's to re-enable a debug interface that's been locked. Basically, anytime there's like a yes or no check where you're trying to change the program flow, you can actually do fault injection through glitching the power supply. So kind of bringing the power supply line low very quickly usually on the core voltage line of a chip. But sometimes you don't have access directly to the core voltage, so you can do it on like the general system voltage. You have to remove some of the capacitors and stuff, so that's not actually cleaning up the glitches that you're trying to do. So something that generally doesn't seem like you should worry about could potentially be an issue. The other one related to fault injection is with a crystal, like an external crystal or an external oscillator, to provide your heartbeat to your system, right? It's sort of like, as engineers, we kind of think about, okay, we need that. We need to put it as close as we can to the chip, and it provides the heartbeat and it does what it does. We don't really think about the fact that, what if somebody removes that, creates their own oscillation instead, say with an FPGA, and then at just the right point when they want, they can inject like an extra pulse in there to cause what I say like a heart palpitation, to kind of mess up the internal logic, to maybe change the program flow, turn a yes decision to a no decision, and then gain access to a system. So those are not typically things that an engineer thinks about, but now we have to, because these advanced attacks are so much easier now with the right types of hardware tools. So, it's hard to anticipate everything.
Sure. And I kind of figured I would have to eat my own words when I said something about power supplies, because you're way more knowledgeable about
it's just one of those things that 10 years ago, it was known that you could do fault injection, but it wasn't as easy. And now it's really easy. Really, you could do it with a MOSFET, and you just crowbar core voltage to ground for X microseconds, and some chips are vulnerable to that. So as time goes on and as technology increases, as attacks increase, it's like we wouldn't have been talking really about fault injection back then, and now we are. So it exactly like how you said it is what engineers are thinking. Like, it's very hard to keep up with exactly everything that attackers are doing, right? We can only do our best and hope that we can learn from existing attacks or attacks on other products that we can then use to make ours better, hoping that nobody hacks us first, which is hard. Like there's an example of, so I'd created the electronic badge for DEF CON 27, which is the world's largest hacker conference. And I designed the electronic badge very early on. We were one of the first conferences, as far as I know, to design like a badge that was electronic and artistic and stuff. So I kind of retired for a long time, came back to do DEF CON 27, and it was a really cool like NFMI, near field magnetic induction communication, and a lot of stuff I wanted to play with as far as the micro BGA and tiny parts and things. So I wrote the code, and it was open source, and people could explore it and see what's going on. And one of the attendees actually found some vulnerabilities in my implementation. So basically, I had some buffer overflows of copying memory and not bounding and not properly, checking for the length of things that I was copying. And then he was able to create this whole exploit chain to essentially, through the wireless communication, execute code on the victim badge, which is cool and really amazing. It took him like 3 years, but it goes to show that even somebody like me who is trying to pay attention to that stuff, and even though I wanted people to mess around with it, I wasn't really 100% focused on security, but it's one of those things that it happens. And when he came out with that, it felt a little embarrassing because, I totally should have caught that. But at the same time, it's really hard to catch every single thing. So from a vendor perspective, from an engineering perspective, in the off chance that you do get hacked, hopefully you don't, but if you do, it's sort of like, it's something that you can't necessarily get angry about, and you just want to say, okay, I made a mistake, and try to fix it, and acknowledge it, because everybody makes mistakes, right? We're only human, and even if you're trying to focus on doing the right thing, sometimes you make a mistake, and it happens. And the larger the product is, the more complex it is, the more chance there is of somebody hacking it, and that's just the way it is. So if somebody finds something, hopefully you can update that, make it better for the next time around, and then make it harder for the attackers, and maybe that turns them off and they go somewhere else, or maybe they hammer on it again and they hack it, and you fix it and you hack it, and it gets better and better and better.
Yeah, I'm hearing something interesting here, because it's kind of the broader trend within the industry outside of IoT and embedded, which is de-siloing and trying to get different groups to collaborate. Like I think the person who's actually doing the hardware, doing the physical layout, could probably have better collaboration with the person who's doing the firmware. And then that guy could have better collaboration with the people who are doing the software and the web interface and everything. And there's just so many barriers that need to be broken down if security really is a priority. And so I think that's where tools like Altium 365 can be really useful, because you can put all this stuff in one place and everybody can check each other's stuff. And it seems like that is really one way to, I guess, help people catch each other's errors, like you've mentioned. I know the open source community, sometimes they will, it's really valuable because people can put their stuff out there. Others can make edits to it. You can clone it. You can make it more secure. You can add features. You can make it better. And it almost seems like hardware teams should kind of take that same approach and model their collaboration out of open source.
That's a great point. And it's funny because a lot of times when we're talking about security, and especially within manufacturing, we want to silo and we want to compartmentalize. We don't want the circuit board manufacturer necessarily to have full insight into our schematic. We don't want a third party who's programming our parts to know what that is going into. And you do want to compartmentalize, but from a design perspective, you don't want to compartmentalize. You want to have your hardware engineer talking to your firmware engineers, talking to the network or application engineers, because they all communicate. So, from a technology level, right? So going back to the beginning of the conversation, your hardware, your firmware, your network, different people are working on those, but the firmware is running on the hardware, and somebody might do something in firmware that the hardware designer wasn't anticipating. They might store credentials, for example, in an insecure piece of memory that the hardware designer wasn't intending that memory to be used for. They might have thought that was going to be used for user data that's not as important, or user settings.
Well, then if the board design is not anticipating that, someone could then come in and get that
exactly.
data
That's
off.
exactly it. So they could basically make use of a firmware level kind of misimplementation or misuse by accessing the hardware.
Well, I think it would be even something that might be innocuous to from the perspective of a firmware developer. But then the hardware guy comes in and says, well, I'm just going to lay this out like I've always laid it out. And if they're not thinking security, or if they're not even thinking, hey, someone could pull these credentials off of this interface because I've left the pins exposed, then it's just kind of
exactly right. And that's why the hardware designer needs to talk to the firmware designer and say, okay, what information do you have? Where do we need to put it? What needs to be treated as protected? What needs to be treated? What can be open? And then even at that network level, how is the system being accessed? Where are those credentials stored? How is the network configured? How do they talk with the firmware engineer to understand all those intercommunications? So yeah, you're right. There's all these little bits that can be attacked, and those are the areas where hackers are looking for those interfaces and kind of the misimplementations or a mistake that somebody made. And if there isn't communication within the team, that's where things happen.
Yeah, I also imagine that there is an important element here to think about, which is like future proofing, because you had brought up that people find an exploit or they find a mistake, somebody finds it, whether it's an attack or not, it gets corrected, they update the application, they update the web app, whatever it may be. But at the hardware level, let's say you have 1 million devices deployed in the field and it's a hardware level exploit, like, what are you going to do? Send a technician out to 1 million different locations to swap out devices? I mean, it seems like at some point, if you screw up the hardware, that's it. And you've got, people got to rebuy 1 million new devices. And there's only so much you can update away in the firmware if you're going the typical, MCU plus peripherals type of architecture that, 90% of embedded systems do that.
Yeah.
And it almost seems like something like an FPGA might be preferable, or doing some of that critical security intensive data processing off the device if the device is constructed in such a way that maybe those interfaces are accessible. What do you think about that?
I completely agree. It's even if you think about software, right? So now we're at the point where every week we're getting updates to our software, right? Patch Tuesday, they call it. And now there's a joke of Exploit Wednesday, because when the patches come out for automatic updates for Windows, people look through those patches and see what was fixed in the code in the operating system, and then create exploits and say, well, why was that patched? Maybe that's some exploitable security thing, and then create an exploit based on the patch. So even in the software space, where patching happens more often, it's still a really hard problem to stay secure. What also happens is people will turn off automatic updates, especially in large installations. They don't want to risk their systems going down by implementing a patch or implementing something without it being tested first. So that's why a lot of this malware and phishing and ransomware works, because it's taking advantage of exploits generally, unless they're 0 days, like we talked about before, they're generally taking advantage of known vulnerabilities or weaknesses that the people who are targeted just haven't fixed. So software, given the fact that you can do network types of updates and stuff, it's better. It's helping a little bit maybe, but from a hardware perspective, that's just multiplied by some huge number, because not only is it harder to do flash updates, like you said, but more importantly, if it is a physical board level problem or chip level problem, you're screwed. And there are chip vendors that will try to implement some sort of patching mechanism. So if there's, say, a vulnerability found in the boot ROM of the silicon chip, this is common for more of the secure microcontrollers, then you might be able to add some code in there to patch that vulnerability, because you're not going to respin the silicon right away. But even those might have problems. But it's something that, a lot of times as designers, we're just inheriting the security or lack of security that was given to us by the chip vendors. And at the time, we might say, okay, chip vendor X seems to have good security. They're protecting things in the right way. We're going to use that device as intended or as recommended by the vendor. And we're secure for X amount of time until somebody finds a vulnerability. And now all of a sudden, all your devices are vulnerable. And that is probably the hardest problem of hardware security from a design side, is once things are in the field, if you can't do a firmware update to fix it, and even doing proper firmware updates and having code signing and verifying that the firmware that you're loading on is legitimate and hasn't been compromised. But the fact of, fixing hardware and replacing hardware is expensive, and generally it's not going to be done. And one example, I'm not going to mention the vendor's name, but one chip vendor has billions of chips that are out in the marketplace in mid-range and low-range, kind of mostly consumer devices, but a very, very well-known chip vendor has a vulnerability in their chip that they know about, but they haven't updated their silicon. I don't know if that's just because they want to steer engineers more towards their newer version that maybe has better security, but whatever it is, the billions of devices that are already in the field are now vulnerable now that this attack is known, which means somebody could go, if they get physical access, they could, for example, extract the firmware or really change the firmware, change functionality. And those things are going to remain vulnerable until the product life cycle goes through, and then eventually those products get replaced, and then there's a new version that comes out. So yeah, I mean, it's a world where, like I said, security is never going to go away, because you're always going to have vulnerable devices. Besides the new devices that come out, you have all the old devices that are vulnerable too. So it really is it's a very, very hard challenge. And I don't envy anybody that is responsible for designing the security of a system, because it is very, very challenging and very hard.
Yeah, so there's something that comes to mind, I guess, at least on the physical side, because that's, really where board designers have to spend,
Right.
90% of their time, unless they're also just happen to be doing the firmware. But at least on the board design side, it sounds like there's a few practical things that are just kind of bare bones Windows Defender level security tactics, bury the critical traces, black out the critical components, maybe use non-specialized packaging so that, it's not so obvious what this particular, component might be. I'm wondering, are there any packages that are actually more secure than others? It would seem to me like a BGA. If you've got your microcontroller, it's in a BGA footprint, only those outer balls are really the most easily accessed, because everything after those first two rows is going to have to go through an inner layer. And if you do it with blind and buried vias, then you can put everything in the inner layers and come up somewhere else, wherever it needs to go. And then as long as you leave those output points concealed, then it's that much harder to physically probe. Or is this just an issue that, like, if somebody tries hard enough, they're going to figure out how to get it?
I mean, a lot of what you just mentioned would be called security through obscurity, right? So if you're scraping part numbers off the board or off the chip, and you're leaving your silk screen off the board, you're burying your traces, you're using BGA or micro BGA, or even say like chip on board, or maybe like a package on package, like you can get more complicated. That basically is just going to slow the attacker down, and it might limit the capability, or it might require more capability to do. So for example, like a BGA part, maybe that's going to turn away some curious high school kids that maybe don't have access to some rework equipment. But if you have access to those things, you can, take the BGA off. You can very easily now make your own circuit boards, right? Obviously with, with Altium and lots of other tools, you can create some sort of interface board, some sort of shim to sit in between the BGA part and the rest of the board and break out the signals that you want. So there are things to do. It just makes it harder. Instead of like soldering wires or tapping onto, a leaded part, or, clipping on with a chip clip or something, you have to think more about the attack process before you do it. And yes, it makes it much harder, but people who are determined will still go after it. But maybe it's like, okay, if I know they're going to target my part, we make it BGA. We use BGA underfill to make it harder to get access to the balls. Maybe you add on all these additional layers. You enable whatever security you can. Maybe you encase it in epoxy as well. Like, it all depends on how long you want to prevent the attacker from getting to it, is what it comes down to. But yeah, it's really like if somebody's determined enough, they will. It just makes it more difficult.
And then I wonder if there's ever any, and this is going to sound like total James Bond kind of stuff, but I wonder if there's any way to, design a device so that if you do try and access it, you actually eliminate all the data or just destroy the critical parts of the device. That happens.
Yeah. So those would be things called anti-tamper mechanisms, and that would be kind of physical security for your electronic system. Generally, we'll see that with like accelerometers for, something's enabled, and wait a second, this power meter on the side of the house, once it's installed and operating, it shouldn't be moved. So if it's moving, it's going to know. Yeah. I've seen light sensors. So if it's, say, a photodiode on a board, and you open the package, assuming that the system's running or is powered in some way to know, it says, wait a second, I see light when I shouldn't. Another really common one is using switches, micro switches of some sort, push button switches, or maybe just, two pins with a connector that gets pulled off when you open the housing. So you can do those things to prevent the physical access. And that really is very similar to a home alarm system, where you have these different things that sense if there is something happening and then respond in some way, which usually is going to be erase memory. Maybe it erases the firmware. Maybe it does physically self-destruct. Depending on what you're working on, I've seen systems that will destroy certain parts of their components or erase certain areas of memory, or more commonly, like remove power from the battery-backed RAM that's storing the critical things. So yeah, those are all things that, especially if used in layers, they're good. Because if you know how that is done, you can generally figure out a way to defeat it, which is why the information gathering stage and that product teardown stage, if you have multiple devices, is useful, because then you can figure out what those mechanisms are and then defeat them to get what you need. And then maybe the next time you attack it, you don't need to do that again. You also did mention FPGAs, and that's something where, personally, from a hacker perspective, FPGAs, I think, are very difficult to work with. So they really do make a great kind of opaque box that if you're trying to offload some critical functionality, or maybe you use an FPGA with a hard or a soft core inside, now you have your microcontroller and your peripherals all in one chip. It changes the attack approach. And it's something where there are researchers looking into how can we reverse engineer the bit streams to figure out what they do. How can we modify bit streams to perform some additional functionality with an FPGA? But it's way harder compared to extracting firmware from a microcontroller, where now you can just look through the code line by line and disassemble it and see what's going on and patch it and do whatever you want. So it is a good, I guess also maybe that security through obscurity if you're just trying to make it harder, but it will definitely make it harder. That doesn't mean it's still going to have a debug interface. It's still probably going to have, inter-chip communication if there's outside stuff. It might have a UART interface for human, boot log information or whatever. So it depends on how the FPGA is used and configured, but it does make it harder, because somebody's not going to go grab a data sheet of the FPGA and know exactly what it does, right? You have reconfigurable pins. You have a data sheet that's 5,000 pages about how every pin can do everything, and how you can configure the logic in a million different ways. That's not as helpful as finding a data sheet that says exactly what each pin does and what peripherals are there and everything. So that is a possibility too, of using an FPGA, or even using an ASIC, right? Of using your FPGA for the design, and then if your volumes are high enough, you start doing some custom chip fab of things as well. And
that's another great point. Yeah, go into an SoC that you can now take full control over in terms of where the interfaces are located on the physical device.
Exactly. Yeah.
How they're going to be accessed.
We haven't even touched on chip level hacking, of decapping the chips and looking at the silicon. That's a whole other world. But FPGA vendors do seem to be more cognizant of that than general purpose microcontrollers, meaning they have had attackers try to decap their chips and find out what's going on. But yeah, decapping and that physical chip level stuff is the next level down, that you run into the same issues that you run into on a board level, as far as identifying signals and injecting signals and patching things and soldering and desoldering, cutting traces, all of that. But now you're at a microscopic level, and eventually you just can't hide, right? If somebody can get access to individual transistors or your flash memory area or your configuration bytes or your secure key storage or whatever it is on your die, it's usually game over. But it also now increases that complexity way more and limits the type of attacker that's actually looking at your stuff.
Yeah, and it seems like, there's so many more vulnerabilities that if they are on an FPGA, they are much easier to reconfigure away compared to the typical MCU plus peripheral type of architecture.
Yeah, especially if it's a hardware or chip level implementation level thing, right? You could try to reload the bit stream and hope that's okay, as long as that bit stream to FPGA kind of interaction is secure, which generally most of the time these days there is some sort of code signing and protection for doing FPGA reconfiguring, as opposed to microcontrollers where not so much.
That's extremely interesting, and you're opening my eyes to this whole other area of electronics design that I don't get enough exposure to. So I definitely want to thank you for coming on the podcast with me. Super, super informative, and I've learned a ton, and I'm probably going to email you personally and ask you questions.
Sure. Yeah. I mean, if anybody watching has questions, feel free to reach out to me also. And, I think the main takeaway for all of this is, as you're designing, as you're having your design reviews, as you're doing every level of your project, just think, what would an attacker do? Why would a hacker want to get to my thing, and what would they want to do with it, right? And if you put yourself in that mindset of every stage, you're going to be much better off than if you just pretend it's not going to happen.
Sure. That makes total sense. Well, thank you again so much for coming on the OnTrack podcast. And everybody out there who's listening, again, this is Joe Grand. I'm going to dig up your previous AltiumLive presentation, and we'll put it in the show notes. We'll have some other links in the show notes. And if you haven't signed up for AltiumLive this year, go over to altium.com/summit and fill out that registration form and sign up. Thanks again, everybody, for watching, and don't stop learning and stay on track.